Okay, so today we are starting a new chapter 4 about weak and weak star topologies. So first we need to remind somebody's coming. Okay, we need to remind some things about topological spaces. And in fact, today we are basically defining the initial topology and then see how the weak topology, in fact, the weak topology is an initial topology of a special kind. So first, some reminder about topological spaces. So sometimes we don't study topological spaces in undergraduate courses. We study topologies which are defined in metric spaces. So metric space, or when you work with a Banach space, a norm. And so metric spaces naturally defined the topology endowed with the metric topology, which is defined with the balls, right? You say a set U is an open set if for every x in U you can find a ball of radius epsilon such that the ball centered at x and with radius epsilon is included in U. All right. Okay, and then you define the open sets, and the open sets are define the topology. But you can also define a topology without defining a metric, and we need that, in fact, to define the weak topology. So in general, you can define a topology without a metric by assuming these three items, which are verified for the usual topology on the metric space. So the three assumptions are that the empty set and the wall space belong to the topology. So the topology is the open set. So topology is a set of sets, and we call them the open sets. And so the second point is that the topology is stable by finite intersection. So if you have U and V that belong to my topology tau, then the intersection of U and V belong also to the topology. And if you have a family, not finite, any family of open sets, then the union is also an open set. So when you have that, you can say that those sets are the open sets, and you have defined a topology. And so when you have a topology on a space X, you can call it a topological space. Okay, it will be, so next, it will be useful to define some special subspace of my topology that we call a basis. So for example, for the usual metric topology, the open balls define a basis. But as a general fact, a subset B of tau is called a basis. So the elements of the basis are open sets. So sometimes we say a basis of open sets or just a basis. If every non-empty open set of X can be written as a union of sets of B. Okay, so here each UE belongs to B, and any open set can be written as a union of sets of my basis. Is that clear? All right, so next, with that in mind, I propose you to solve this little exercise. I put you the definitions just in case. All right, this is a small exercise, and you have just to write it down, but you have to do that to get into the things. So yeah, just do this exercise, please, and we can talk after that. Okay, so assume first that B is a basis of tau. So we want to prove 1B. So let U in tau and X in U. So you can write so by definition of a basis, we can write U equals, so U can be written as a union of elements of my basis. So I call them Vi. All right, so but next, since X belongs to U, there exists I in I such that X belongs to Vi, which is including U. So 1B is therefore verified if 1A is verified. So 1A implies 1B. Any question? All right, next, we want to prove that 1B implies that B is a basis of tau, which is, we can write every open set as a union of elements of B. So let's do that. So let's choose a U. So I want to use 1B. So in order to use 1B, I'm writing U as the union of all its elements. So I say that U is the union of all its elements. But now, thanks to 1B, I can write that so this is included in union of X in U of Vx, and such that X belongs to Vx, which is included in U. And this is included in U. And Vx in B. Okay, so we just proved that U equals the union of, you can write U as a union of elements of B. So therefore, B is a basis. Okay. So next, to prove the second statement. So assume that U is an open set, then the conclusion is just 1B, right? It's the same thing. So if U is an open set, then for all X in U, there exists BV in B such that X is in V included in U is just 1B, so it's done. So conversely, if let U a set in X. So let U be a subset of X. So if U satisfies the assumption, then we can write, so satisfying, let's write it, satisfying that for all X sorry, for all X in U, okay, then I write again U equals the union of X in U of X, which is included in Vx, which is included in U with Vx in B and X. So which proves that, so it's very close from the one, which proves that U equals union of the Vx, but since Vx is in B, Vx is an open set. So therefore, U is in tau as union of, so U is an open set as an union of open sets. And that's it. So next we can compare different topologies. So you can have different topologies on the same space, and we can compare them. It's a partial order. There was a question at the beginning of these lectures about partial order. So you can also when you have two topologies on a set, on a space, you can compare them, and you say that a given topology is coarser than another one or weaker if, so a topology tau1 is coarser than tau2 or is weaker than tau2 if, okay, if every open set in tau1 is an open set of tau2, meaning that in this sense, tau2 has more open sets than tau1. You can also say that tau2 is finer because it has more, it's more refined, it has more open sets that are stronger than tau1. Okay, so the definition is here with a small typo here to be corrected. Okay, so next. So what we did up to now, so we recall what's a topology, and when we have a topology, we defined what is the basis of a topology. But now the question is, maybe I can first define a basis and then define a topology associated with this basis. That's the case. So that's what we are going to do now. So assume that, there's a question. Okay, so so if you have a topology and a basis B associated with this topology, then 4.1 and 4.2 are verified. So 4.1 and 4.2, how it reads? It reads that for every x in X, you can find U in the basis such that X is in the basis. Why is that? Why? It comes from the fact that the whole space is an open set, and then it comes from 2. Also, if you have U1 and U2 in B, and if you have X in the intersection of U1 and U2, then you can find U in B such that X is in U is in U1 is the intersection. Okay. Yeah, so this is natural. I let you find out why. But conversely, if B is a subset of part of X, So if B is a set of sets in X that satisfy 4.1 and 4.2, then there exists a unique topology tau on X for which B is a basis. Okay, so prove all these things. Try to prove all these things. So assume that tau is a topology and B is a basis associated with this topology. Then, so for topology, since X is an open set, there exists U in B such that, so for all X in X, there exists U in B such that X belongs to U, of course, belongs to X. So yeah, 4.1 comes from the fact that the whole space is always an open set. All right. So as for 4.2, comes from the fact that also U1 and U2 are open sets, so that the intersection of the two is also an open set. Okay. So now, conversely, we want to prove that if some subsets satisfy 4.1 and 4.2, then there exists a unique topology for which B is a basis. So if you want to define a topology for which B is a basis, we don't have much choices. We have to choose the open sets such as the open sets right as a union of elements of B. So that's our topology. So of course, a topology, the empty set is always in the topology, so that's done. Now we are considering the non-empty sets, and let's define U belongs to, U. So we define the topology tau as follows. So U belongs to tau if and only if you can write it as a union of elements of B. So you can write it Sorry. Okay, so you define your topology as follows. U is an open set if you can write it as a union of elements of B. If you cannot write it, it's not. Okay. So, but we have to prove that when we do that, the union and the intersection of my open sets are still open sets. That is, my definition is stable by union and intersection. Okay, so 4.1 ensures that X is an open set of this topology. Okay, so if 4.1 is satisfied, then X is an open set of you can write X as a union of elements of B. Okay, I don't write that, I let you write it. So now I'm concerned with the union and intersection. So so assume that my elements of tau satisfy what I just I've written. And so if I look at the union of some elements of tau, by definition, I can write it as each UI, I can write it as a union GI of UJ with UJ belongs to B. So if you can write, if you have a union of UI and UI is itself a union of elements of B, then the whole thing is a union of elements of B, and so that tau is stable by union. So if UI belongs to tau, so the union belongs to tau. Okay, now let's do the intersection. Finite intersection. So let's do two things. So now assume U1 and U2 are in tau, so they are open sets. So you can write U1 as union of U1I and U2 as another union. So J to J. And you look at the intersection of the two. So this is so you can write it union of UI J in J of U1I intersection U2 J. But now I use the fact that I use 4.2. So in fact, I can, so by using 4.2, I can write it as union I in I, J in J of, and here, this is the trick. I wrote it as the union of X belonging to U1I, U2J of some Vx, where Vx is in B, and X belongs to Vx belongs to U1I, U2J. The point is, I don't know if the intersection is not, the intersection might not be an element of B. For example, you take the intersection of two balls, it's not a ball. But thanks to 4.2, you can write it as a union of elements of B. And so again, here, this writes as a union of elements of B, which means that U1 intersection of U2 falls into my definition of the topology. So we're done, because now a union of elements of tau is in tau, and a finite intersection of elements of tau is also in tau. Also, I said that I said yx is also in tau, and we adjust the empty set, and then we have a topology. And you have no choice. It's unique because it's exactly defined as the union of elements of B. If you had some other things, it might be also a topology, but B will not be a basis of it. So we're done. So now we are going to define the initial topology. In fact, we worked for that. And we are defining the initial topology because we're working in order to define the weak topology. So I'm going to read that and to discuss that. So what is the initial topology? So you start with a set, and you have also a family of topological spaces. So you have a set E and a family of topological spaces Fi endowed with a topology tau I. And you assume that for all I, you have an application from E into tau I, into Fi. So now you define a set B of sets defined as finite intersections of so you look at an open set, you look at the open sets on the Fi's. And then you take Fi minus 1 of the open sets. Okay, so your elements in B are defined as a finite intersection of the sets Fi minus 1 of an open set in Fi. Okay, then when you do that, B satisfies the assumptions 4.1 and 4.2. I'm going just to read why is that. This is also a small exercise, but at this time I will just read with you. So, so first of all, if you look at phi I minus 1 of the whole set, it's nothing but E. So you have your 4.1, right? So because so this by definition is in B, but this is equals to E. So this gives you 4.1. Now you want to prove 4.2. So you want to prove that for any U1 and U2 in B and for X in U1 in the intersection, then you can find some V such that X belongs to V, belongs to the intersection U1 intersection with U2. So let's say what the meaning of this complicated notation. So by definition, what you want to write, you want U1 is a finite. So here J1 are finite. It's a finite intersection of elements of this kind. Okay, so you write U1 as a finite intersection of phi I minus 1 of some open sets in Fi. And U2 is the same. So, but now if you take the intersection of 2 is nothing but an intersection also. So by our definition of B, U1 intersection with U2 is also a finite intersection of this kind. Okay. So that's it. 4.2 is also verified. So now how we define the initial topology? The initial topology on E is the unique topology for which B, as defined as above, is a basis. Okay, so that's very good. And we can remark that by construction, the initial topology is the coarsest topology that contains the reciprocal image of the open sets in the Fi, in the tau I. Okay, so that means what? That means this is the coarsest topology that makes the Fi continuous. All right, so now we're good to define the weak topology. So now we're coming back what we were doing, meaning that we have a Banach space E. And on this Banach space E, you have, for example, linear functionals, continuous linear functionals with value in K. We use that a lot. Now, I want to define a coarser topology. Yeah, because if it has less open sets, it will have more compact sets. So for analysis, it's useful to have a weaker topology. And so the weak topology, and we call it sigma, so it's a topology on E, is the initial topology associated with the linear functionals F in the dual E prime. So that's the definition of the weak topology. It's an important tool in functional analysis. Okay. Okay, try to solve show that the topology associated with the usual norm on E, so now E is a Banach space. So the usual topology on E contains more open sets than the weak topology, meaning that every open set of the weak topology is also an open set for the usual topology. So try to reflect on that and come up with a solution.